Hello everyone, my name is Vicente Martín from the University of Seville, and I will present the work called Rolling Effect in Fretting Fatigue Test at the crack initiation stage. Fretting fatigue is very often material damage in mechanical contacts. This surface damage caused by small oscillatory displacements, which are the consequence of friction between mating surfaces, and small surface cracks appear at the contact zones. These cracks can grow until the complete fracture of the component. Due to the presence of a tangential load and considering the stiffness on the contact pair, in some practical cases a small rotation can be produced between the mating surfaces. Although cylindrical contact is not the typical setup used in engineering components, it is a widely used contact pair in fretting fatigue test. In this type of contact pair, where the rotation leads to a small rolling between surfaces, being this effect more or less important depends on the contact pair stiffness. In the past, we did a fretting fatigue test campaign using a cylindrical contact pair. The result of the fretting fatigue test showed a bigger contact zone than the contact zone given by the theoretical width, owing to the fact that the fretting fatigue bridge produces an effect of rolling on the contact path, which increases the contact zones. Additionally, and in order to be sure that this increase in the contact zone is attributable to rolling, the theoretical contact width was measured in a test having only normal loads. We observed that this contact width had values very close to those given by the Hertzian contact theory. The fretting fatigue tests of the campaign conducted in the laboratory are shown in the left figure. The specimen in the middle is between two contact paths. First, normal load N are applied, and they are kept constant throughout the test. Then, sinusoidal load P is applied, and a stress is produced on the specimen. At the same time, tangential load of reaction Q appear in opposite direction to load P on both contact paths and are sinusoidal too. The specimen has a section of 10 mm with thickness of 8 mm, and the contact path have the same thickness and a radius of 100 mm. The coordinate axes are as follows: the x-axis along the specimen, the y-axis perpendicular to the surface, and the z-axis marking the thickness of the specimen. A contact path is shown in the image. The contact zone is measured on the contact path because the specimen broke after the test and didn't allow the two pieces of the specimen to fit together. The photo shows a 2D image of the contact path and it depreciates the curvature of the path, therefore make it possible to measure directly on the image. It shows a smaller contact zone thickness than the specimen thickness and is measured to calculate the experimental width, called in this work 2AR, A of rolling. The method used to measure the experimental width 2AR is the division of the area measured by CAD software by the contact zone thickness. The contact zone thickness is considered a constant value. The method attempts to approximate the contact zone to a rectangle. This rectangle has the same CAD measure area and the same thickness as the contact zone. The other side of the rectangle is the mean value of the contact width 2AR. On this slide, the information of the three tests analyzed is represented. The first table shows the value of the loads N, Q, and sigma of each test. This table also shows the life of the test done, the theoretical semi-width, the theoretical pressure, and the range of the axial stress. The second table represents the measured experimental semi-width AR and the theoretical semi-width AH. You can see in the fifth column the ratio of AR divided by AH. The angles of rolling are calculated by the difference between both semi-width and are shown in the sixth column. You can see in the figures below the difference between the two cases, the no-rolling case on the left with AH on the concentrated edge and the rolling case on the right with wider AR caused by the rotation of the path. Finite element method analysis is used to calculate the stress and strain field. The analysis is simplified in 2 dimensions and uses plane strain. In the first step, normal load N are applied and they are kept constant throughout the analysis. Then, the stress sigma and the tangential load Q are applied at a time and in opposite direction. Also, the angle of rolling calculated on the previous slide is used to rotate the path in phase with sigma and Q. The contact width obtained by FEM analysis is the same as the experimental width. 6 load steps are applied and the steps 4 and 6 are compared because the analysis gets stable. The loads N asterisk and Q asterisk used in the analysis are divided by the thickness of the specimen. Here you can see some results from FEM analysis of the 3 tests showing the effect produced on the specimen by the rotation of the pad. The first line of graph shows the contact pressure on the ordinate made dimensionless by the theoretical pressure. In this plot, the x-coordinate on the abscissa is made dimensionless by the Hertzian contact semi-width. This graph shows 3 plotted lines. The black one is the non-rolling case and is centered, and the red and blue lines are a cycle for the rolling case, to the left when it is in contraction and to the right when it is in compression. The stress and strain field vary for the rolling case due to the fact that the pressure changes in the rolling case. The second line of graph represents the range of the axial stress on the ordinate made dimensionless by the theoretical pressure, and again the x-coordinate is made dimensionless by the Hertzian contact semi-width. The graph shows 2 plotted lines. The black is the non-rolling case that represents the hotspot on the contact trailing edge, as the theory states. However, the green line represents the rolling case and shows instead of the hotspot a zone where it is difficult to know the point where the crack initiates because the zone has almost the same stress values. Here, the method applied is the same as the one used for the measurement of the contact zone area on the contact paths, where the area was approximated to a blue rectangle to obtain the mean value of 2 AR. The only difference here is that the measurement of the area on the specimen is done up to the crack edge. The green rectangle is the approximation to this area. After top side of both rectangles being aligned, now it's possible to use the center line of the rectangle to measure the mean value of the x-coordinate of the crack from the center line to the bottom line. The value measured for each test are smaller than the Hertzian contact semi-width, and this is due to the fact that the cracks are initiated within the contact area and not at the contact trailing edge as the theory states. On the following slide, we are trying to analyze which parameter is able to capture properly the hotspot when the rolling is considered. In the first column of graphs shown here, you can see a cycle strain range of each test in the axial direction. Note that in all the graphs is the x-coordinate on the abscissa made dimensionless by the corresponding experimental semi-width of each test, AR1, AR2, and AR3. The second column of graphs shows on the ordinate the maximum normal stress in the axial direction, and on the third column shows the Microscope parameter that is the result of a multiplication of the first and the second column of the graphs. Looking at the plots of the strain range, you can see that the hotspot is inside the contact zone, but near the contact trailing edge. This is a very important fact because if the no rolling is considered, this parameter predicts that the most damage point will be on the contact trailing edge. On the other hand, direct stress also shows similar trend, but the hotspot is farther from the contact trailing edge than before. Finally, you can observe the prediction produced by a common parameter in fretting, the Smith-Wasson-Topper parameter, where the results are very similar to those obtained by the direct stress. In addition, the crack initiation point for each test are shown with a vertical line, where the cracks initiate, grow, and finally leads to a complete fracture of the specimen. You can see that neither direct stress nor Smith-Wasson-Topper are able to capture the hotspot. Meanwhile, the strain range produces reasonable results. Now we can focus on the crack initiation path in the fretting fatigue test because the stress and strain field are changed with the rolling effect, as you could see on the previous slide. The Smith-Wasson-Topper and strain range parameters are used to calculate the crack initiation angles inside the test specimen for the non-rolling and rolling case. First, the critical points are defined for both cases. The theoretical contact edge is used for the non-rolling case, and the mean value of the experimental crack initiation is used for the rolling case. The parameters are calculated along each of the lines from theta minus 90 degrees to 90 degrees at discrete point, but with the peculiarity that for all of these points, the orientation of the material plane considered to evaluate the parameters are not the critical plane, the critical one, but is the one with the same orientation imposed by the theta orientation. Then the average value of the parameters along each line are calculated, and the line having the highest mean value of the parameters are considered to be the most likely to initiate cracks. The right graph shows on the ordinate the value of the Jesús parameter and the angles where the parameter is calculated on the abscissa. This graph shows the result of the three tests with no rolling and rolling effect. As you can see on the table, for the no-rolling case, both parameters show the maximum values and almost vertical plane. Then, in the rolling case, the Jesús parameter shows small angles than the ones of the strain range parameters. The positive values are oriented to the center of the contact. The maximum value of the parameter represents the critical planes where the cracks possibly initiate. Some measurements are done to verify this result, as you can see on the next slides. The initiation cracks angle are measured with a confocal microscope to obtain three-dimensional maps of the cracks that cause the test specimen to break. An example of this is shown on the image where the measured area is 0.4 mm by 0.24 mm. On the left, there is the same three-dimensional map with three parallel intersections in blue, which will be seen on the next slide for the three test specimens. This intersection in blue represent the profiles on the crack in different points. These cut planes will be around points where the cracks possibly initiate. In this graph, you can see the crack profiles, which were measured using the confocal method explained on the previous slide. These profiles are represented in true extent with the same coordinate axis used in the specimens. The thin lines in green color represent different intersections for one confocal measurement, and the thin lines in blue represent the intersection for another confocal measurement at the same specimen, but in a different zone of the crack. The thick lines in green and blue are the mean of the lines with the same color in each graph. Two pairs of straight lines in red and black represents the initiation angles of the Jesús and strain range with the no rolling and rolling effect calculated in advance. The strain range with rolling effect is represented with black dashed line and is the one that is the most approximate to the experimental profile measured with the confocal microscope. Corroborating that, it is interesting to consider the rolling effect to have better prediction on the crack initiation angles. The first conclusion is that the fretting fatigue bridge produces an effect of rolling on the contact path, which increases the contact zones, and this changes the stress and strain field. The second conclusion is that the cracks initiation do not appear at the contact edge as the theory states, but within the contact zone, as you could see through the experimental measurements, and this was verified by the finite element method analysis. Finally, the crack initiation angle has been calculated by using two parameters, strain range and Jesús, and this angle have been compared with the specimen measurements. By this comparison, it's possible to see that the strain range parameter with the rolling effect has more resemblance to the specimen measurements. Thank you for your attention.